So I think we have now time for have a discussion, a general discussion. Please unmute yourselves or raise your hands if you have any questions for either Jake or Mariana. Maybe if there is no questions at the moment, let me start. I will. Jake, can I ask you a quick question? So in the interferometer protocol that you turn on the lattice, we know that there are going to be contact interactions. And in principle, these contact interactions can depend on temperature when you go to D wave. I mean, if they're very small, you have S wave leading order, but depending on the temperature of the atoms, you can have higher order terms. So is there any way that you can, I mean, how we're going to get rid of that, or how you distinguish what you are seeing from deviation from those type of interactions?
So I think what I want to be clear about is the trouble that comes into play when you're trying to build an atom interferometer is first you try and make it so it's in the non-interacting region. Now we don't always succeed, and particularly for long hold times, it becomes hard as you're getting it. Though I will say, Holger's results so far actually suggest that it works and S wave isn't an issue. But the next point is the actual protocol is looking for the collapse of coherence and then revival. And so I guess my question back to you as the atomic scattering expert is, under what conditions am I going to get a revival of coherence of the atomic cloud after I got the destruction from the S wave portion?
Well, depends. I mean, you can have effective one-axis twisting models that are a little bit integrable, and you might have collapse and revivals. But
yeah. I mean, but the other point is that whenever you do these types of experiments, it's crucial to show that your signal is from gravity.
Yes, exactly.
Right. So when I talk about doing these experiments, you do the atom interferometer, and you have to move the mass system, right? Because you can move it so that it doesn't have a strong effect, or move it so it has a strong effect. Like displacing where the atoms are doing the interference by small amounts, as you pull out the gravitational effect from self-interactions in the atoms and other terms. And so I just want to be clear, like you're not just looking for collapse and revival, you're looking for collapse and revival that depends upon where the masses are located.
Okay.
I hope that helps.
Okay, great, thanks. Yeah. So I see another in the chat, there is questions. So, I mean, we are in a discussion period, so please unmute yourself and ask the questions. That's easy. I mean, I think, Amine?
Yeah, thanks. Yeah, so just wanted to ask Mariana if she can briefly mention this point she raised about detecting fifth forces using atomic spectroscopy.
Yes, this is actually a very interesting recent idea. And the idea is to use isotope shifts. So to use the system in which you can have a lot of isotopes, for example, terbium or calcium. And then what you actually look for, you need at least 4 isotopes and at least 2 transitions. And you build what's called a King's plot. And in this case, according to the normal standard model, generally, it always assumed to be linear, and it allows you to separate different kinds of isotope shifts, the field shifts versus mass shifts. It was shown that you have some sort of a fifth force, you cover-like type coupling, that this plot will become nonlinear. And that's why you need at least 4 isotopes, because then you can actually, instead of the linear type plot, you can actually look at the deviation from the linearity. So the great thing that you're not comparing experiment to theory, because such precision theory for isotope shifts is actually not possible at this level. So what you're comparing is essentially whether that graph, if you're plotting, whether you will have a deviation from the linearity. The problem which you run into is that there is a standard model signal which is nonlinear, and that have not been yet fully quantified. And in this case, however, we actually, with a number of collaborators, submitted a proposal in that to both actually look for precision measurements and for to look for those standard model nonlinear effects. The great thing is that the more isotopes you get, the more of them you can measure. So if you can have 4 isotopes, if you, for example, can have measurements in 6 isotopes, then you can actually get rid of some of the nuclear physics parameters. Things like QED or eventually parity violation would also be nonlinear, but that had been estimated. So you have kind of two cases. For example, calcium, when you have lots of isotopes and you expect more or less it to be linear, or you can have a terbium when your nonlinearity signal would be larger, but then you have even more isotopes and you can probably measure them away. And in this case, you eventually would have to use non-stable isotopes because you just don't have enough stable one, and you have to use isotopes with spin 0. And that's a basic idea. It's very promising. It's one of the ways to reach the parameter space for certain types of the fifth force interaction. That's a scalar type of interaction. It's meaning that people haven't yet figured out, I think, how to look for spin-dependent interaction that way. If we do, that actually be also particularly interested. But that's a basic idea. You need a lot of different transitions and a lot of isotopes. And also using highly charged ions, you can actually have much easier theory, because in this case, you just have fewer electrons in there. So it doesn't really matter. You can combine measurements in ions, highly charged ions, and neutrals in this case.
Thanks, Roland.
Please go ahead, Andrew.
Yeah, really nice talks this morning. I had a follow-up, I guess, to the previous question for Jake about the atom interferometer with the lattice implementation. So just wondering sort of what length scales separation distances from the atoms to the mass we're thinking about. And I'm thinking about this in the context of trying to isolate only gravitational interactions from other kind of backgrounds, which might otherwise produce signals.
So actually, there's 2 points there. First of all, length scale-wise, we think a lot about this sort of 10 micron to 10 millimeters as the range of feasibility. So below 10 microns, the C6 coefficient is just too big, and you're going to be dominated by that. Kind of getting atoms to be coherent and hold them for length scales on the order of millimeter becomes very, very challenging. So that's kind of the range you get to play with. I will say that actually the non-gravitational interaction dramatically improves the experiment. And so we call this pre-charging, if you will, or amplification. So if you're familiar with quantum metrology, you know there's this idea of like Fisher information. And there's like the maximum extraction that you can do for a particular parameter. And so in single atom physics, if you already have an atom with the coherence, then it's easy to drive that coherence around. But to create the coherence is quadratic in amplitude. Once you have it, then it's linear in drive. So actually, if you have a C6 type coefficient, which causes these things to entangle with masses, and a gravitational interaction, and you can flip the sign of the interaction, which you can do by starting with the atoms in a metastable excited state and flipping them down, or alternatively using a magnetic interaction, then you can actually take the integration time requirements down by orders of magnitude, because you can get yourself in a pre-entangled state and then sort of increase and decrease that entanglement a small amount from the gravitational portion. And by seeing the decrease followed by increase, you can still get the same proof output. So anyway, I want to mention that actually having some interaction is not bad by itself. And in fact, it can be a benefit. The trick is distinguishing them. And there you're really relying on long-range physics, which means it's really, really critical that your atoms not be charged. But the good news is with atoms, that's easy. With masses, it's hard to know whether they're charged or not, but even one over R4 is going to be fine in this setting.
Thanks. And then as far as how well you know these other interactions, to the extent that you can tune, parameters and whatnot, how important is that in terms of these are much, much bigger signals, right? So
yeah. The short answer is they're very important. Conveniently, there's this sort of Ramsey interferometric signal from the differential acceleration, which is a background, which allows you to calibrate where the masses are themselves. And then you're looking for this Clapton revival on top of it. So there's sort of 3 stages. My sense, and I've been talking with Holger about it a lot, is that the first experiment is something that's actually quite doable today, but it has loopholes, right? And so the experimental program is really closing loopholes over the course of 10 years to really go from a proof of principle to something that says, oh, now we're down to the base assumptions. Then we need to make better assumptions. That's my take on it.
Thanks.
Great. Igor,
Yeah, thanks. Thanks. Excellent talks, both of them, and thanks for organizing this conference. So my question is actually very related. So that's a good fit. So it's for Jake. Half question, half comment. Namely, also specifically for this proposal for using entanglement and then look at these collapse and revivals. It relies on these revival peaks. And like you mentioned, the temperature actually is even of the surrounding could be beneficial in some sense. But this is reminiscent. So the comment and the question is the following. It's reminiscent of something that's also done in the work on collapse. So one of the first proposals was the Marshall et al. Proposal by the Baumeister group and Penrose, where they also look at this collapse. And then we had a follow-up work at Kleckner et al. In 2009, where actually when you look more closely about when you have the temperature, even though it looks like it helps you, it closes the bandwidth of where your revival comes in. So it makes the revival extremely narrow, such that actually at even small temperatures, you already have too narrow revival to actually resolve. So I'm not sure if you looked at this kind of revival narrowness to see that there is actually limitation on temperature. It makes it a bit more difficult.
Yeah, so thank you. So one of the key points, the reason that temperature helps you in these types of proposals is that what's happening with the atom is putting an impulse on this object. And the impulse translates to energy as the momentum plus the impulse squared. So a thermal state of the oscillator gets more energy per impulse because it has a higher initial momentum. But at the same time, I need to maintain my assumption of this time translation invariant channel. And that means that I can't just prepare the oscillator in some high momentum state. It has to be thermal because that's my time translation invariant channel that keeps it in that state. And so the assumption requires me to use the thermal state rather than a prepared state, just as a side note. But then in terms of the narrowness of revival, I don't know what you mean by narrow. I've got to be completely honest. I will say that the revival is a very small feature, right? It's not a lot of collapse and revival. So that you have to, this is why pre-entangling, for example, helps a lot.
So to clarify, narrowness, I mean in time. So to time resolve, because the revival is exactly at the full period.
Yeah,
and so that that becomes extremely narrow at higher temperature. That is the limitation that comes.
Actually, the limitation for higher temperature that we find before we get to the narrowing problem. So we have pretty broad collapse and revival right now because it's very weak coupling. The actual limitation is that the thing starts moving too much. So there's a physical length scale which you can allow this thing to oscillate around. And if it moves too much, then your assumptions in the experiment break down, right? Like it starts to impinge upon the optical beam. So actually we found that once the scale of temperature where it starts moving around on the order of a micrometer is probably the limit from other considerations before you get to the narrowing that you described.
All right, so we are approaching the time for a break. So, but let's discuss the last. I see one hand raising. Is that correct, Anupan? There is a hand raised there, or it was the prior one?
No, yes. So I just wanted to comment. I think what Igor and Jake. I think so. One of the key issues are this decoherence, and I think, but nevertheless, these are all classical effects. These are not quantum effects per se. So in principle, you can, if you know your background extremely well, you can get rid of all these effects in a way. These are not really because of any quantum fluctuations, which is causing your dephasing effects.
So just to be very, very clear, I stated the two critical mathematical assumptions. And what you're talking about is in the first assumption, the time translation invariant channel. So when you talk about classical noise, you're talking about noise that has this time correlation in it. And if you measure it and then start the experiment with a particular measured value, right, and then go forward, then you've actually made a channel that's not time translation invariant. So it breaks the assumption, which is why I said there's loopholes, and you have to keep cutting out the loopholes over time. So anyway, I encourage you, if you want to we had a loophole table in our paper, and that's one of them, right? Like that, indeed, this assumption of time translation invariance to prove that you have a time translation invariant channel is quite challenging, The best way I know to do it is to actually show that the channel is fully thermalizing. And then you can deduce from that fully thermalizing property that is time translation invariant. But then you have the whole experiment. The problem of the experiment becomes not showing Clapeyron revival, which is hard, but it's actually showing that the mass is in this sort of purely thermal environment. And so we've done this experimentally with opto-mechanics up to about room temperature in the last few years ago at NIST. So it is possible, but it is damn hard. Pardon my language.
Great. So it has been very nice discussion. I think let's us break. I mean, I know that this discussion in some are exhausting, so let's prepare ourselves for the very nice, exciting talks in the morning. So let's us recombine at 10 a.m. where we are going to have Dave's talk. Yes, we will be all back in just 8 minutes. Mm-hmm. Thank you very much for the nice discussion, and see you in a bit. Mm-hmm.
Thanks all.